Yeah, good morning to the last session of this exciting conference. And it is my great pleasure to welcome Jochen Hanebeck of Infineon. Let me say a few words about him. He was born in 1968 in Dortmund. He studied electrical engineering at our university, RWTH Aachen University. And he graduated here with Professor Heimer. Some of you will still know him. He has been then with Siemens AG, which turned into Infineon. So he had several steps within Infineon AG. And finally, now he is the CEO of Infineon. Please give a warm welcome to Jochen Hanebeck.
Yeah, thank you, Professor Waser, and it's great to be back. Actually, almost exactly 30 years since I graduated. So I walked down the Pond Street yesterday. All the shops changed. My favorite bars changed. The places where we got drunk after the exams changed, but still the city feels the same. Anyway, I would like to give you a bit overview on semiconductor trends, in particular artificial intelligence. Please do not expect now inputs to your scientific work, but maybe the overview helps and can tell you where the industry is heading and what are the opportunities which we see. First of all, why semiconductors? Semiconductors are essential for the two megatrends our societies, this planet is facing. I think it's common know-how by now that without semiconductors there's no decarbonization, there's no digitalization. The two trends go hand in hand. Decarbonization will not work without digitalization. And the purpose of decarbonization, I think, we all agree, is to leave behind a planet for future generations worthwhile living in. Now, what can semiconductor contribute to solve these mega challenges in our industry? And here I came up with a picture which might be new to some of you, but it was essential to explain also politicians what it's all about with semiconductors, because everybody talks about the nanometers, and we know all Gordon Moore's law, and which is in this trunk, the picture I've chosen, the main part, driving down along geometry into, by now, 2 nanometers and below. That path obviously is driven by lithography, but by no means you can build systems only with microcontrollers or microprocessors. You need a lot more semiconductors, and they are depicted here in different branches. And the important message is these are not legacy semiconductors, these other branches. They are as essential for systems as the main trunk because we need, besides brain, we need power, we need sensors. And if you walk along the tree, you see on the right-hand side power semiconductors, which is one focus area for Infineon. And by the way, also very strong, real stronghold in Europe. Then you see the memories. We used to do memories, but no longer. Then the main trunk, of course, with microprocessors and microcontrollers. By the way, the European market share of the three big players, NXP, ST, and Infineon in microcontrollers worldwide is more than 50%. And if you see here 28 nanometers, the latest generation for automotive from Infineon is made also out of a cooperation with Aachen University, with Professor Waser's institute. RM is part of the 28 nanometer generation. If you walk through the tree further on, it's about wireless, it's about sensors. You might say, yeah, it's a bit rough, but again, the purpose of this tree was to educate politicians that there's more than lithography required in there. And on the sensor side, again, Europe is a stronghold, and I will talk a little bit about quantum sensors, which I think is a great area also maybe for academic research, because there's a lot going on. And finally, the tree ends up with optics, and of course, we all know the roots of the tree was the first transistor, 1947, Shockley, Baldwin, and et al. Winning the Nobel Prize 8 years later. Now, let me dive a little bit into the miniaturization or the Moore's path of things, what's going on there, and then I will talk a little bit about quantum and power. Now, again, first message is each semiconductor type requires a certain geometry and there's a certain fit. And for example, power semiconductors, as you can see on this chart, they are not determined by geometry. They are mainly determined by materials. And I come to that in a minute. There are the advanced microcontrollers, as I said already, a stronghold of European companies. And that's probably what's still is called up to that level more than Moore. And then, of course, we have the microprocessors, the GPUs, and so on and so forth. Here again, Europe has strong contributions with ASML, but I would also call out IMEC. And again, a system is only complete and will work with all three elements. As I sometimes say, there is no brain without power, but also be careful, power without brain is dangerous. Now, what's going on in these geometries? Well, that's what you read in the headlines of the newspapers. The development of product generations as well as fabs is going up exponentially. If you look at the latest generation, if you want to build a 2 nanometer fab, your ticket is 20 billion. If you want to have a respective product family, you are also by now into the billions. What does it mean for the industry? Well, it means that first of all, high investments, of course, but then this was also driving consolidation in the industry. It drove initially the emergence of the foundry industry, but of course also further consolidation, which at this moment in time slowed down due to geopolitics. But it's a simple matter of fact that not every company can afford everything, as maybe Siemens did in the early days of and others of semiconductors, venturing into all branches of the tree. But besides consolidation, the effect out of this curves is that all companies focus to become in one of these branches really a top 3 company. Talking about power semiconductors. And power semiconductors, yes, there is a bit about geometry in there, more on the vertical dimension than on the horizontal dimension, but it's mainly about materials. And here, I think, many of you, at least in my generation, we worked on compound semiconductors in our Diplomarbeit and whatever. Finally, I mean, there was a spot for high frequency, in high frequency for compound semiconductors. But now, after many, many years, compound semiconductors are really becoming mainstream beyond high frequency. And I will talk a little bit about gallium nitride and silicon carbide, and potentially the next kid on the block could be gallium oxide. You see the physical parameters, and you see big differences here in thermal conductivity, for example, for silicon carbide. So looks very, very interesting, but I tell you, to handle silicon carbide is on a lab scale one thing, on an industrial scale is another thing. Nevertheless, the industry is going into that direction. We are building dedicated factories now for silicon carbide, but the material is anything else but easy to handle. Furthermore, if you have a semiconductor with very good thermal aspects, you need to get the heat out, right? The system design becomes the bottleneck in terms of thermal dissipation. Similar challenge, gallium nitride, you see, high on electron mobility, great, but to manage these potential frequencies, you have to change the systems. It's about algorithm, it's about drivers. So the whole thing becomes more and more a system play rather than a simple technology, even though, of course, the root of the innovation is here in the technology, but to make it applicable, to make it work in the application, a lot more is required. Now, on the right-hand side, you see where we see the three materials being placed in the application space. Don't give up on silicon. Silicon is damn cheap. So there's always going to be a race between the compound semiconductors and silicon. The only way or the only reason to choose a compound semiconductor is still the system benefit. On a square millimeter base, we are far away from any cost crossover. So, as gallium nitride is somehow emerging, right? The silicon carbide market is already a couple of billions big. I chose one picture to give you a feeling where gallium nitride is now coming in beyond the RF part. And one area you can experience yourself, if you have a charger for your smartphone, laptop above 100 watts, it's very likely going to be already today gallium nitride. So that's in the market. We see it also coming in onboard charger in the cars. They are currently in transition from silicon to silicon carbide, but in terms of power density, gallium nitride will make the race towards the second half of this decade. Also in low power motor control, if you think about robotics, one of the challenges in robotics is to have small motors for all the joints. And if you think it through, with gallium nitride, higher switching frequency is possible, therefore smaller subsystems are possible. So also a very interesting area for gallium nitride, and also in residential solar, some topologies call for gallium nitride. So a lot going on, and again, maybe gallium oxide is the next thing, but at least that's my last information. It's currently on 2-inch, and you can imagine that's a big headache for industry, which would love to produce everything on 12-inch in order to get cost down, which is essential to push the crossover towards compound semi further. Yeah, talking about quantum sensing, and here I could probably spend a whole hour, but I will reduce it to the following. For me, absolutely fascinating what can be done. Nitrogen vacancy in diamonds, silicon carbide, color centers. I think deep research is done. What is now matters is again prototyping, industrialization. I personally believe that quantum sensing will create earlier revenue than quantum computing, because some of the dedicated use cases, be it atomic clocks, be it magnetometers, be it inertial sensors, are not so far away. And if you're looking for additional and I will come to a motivation why you should spend your time on neuromorphic chips or architectures. But if you are looking for more academic research fields, I think this is an area, and also an area where we have, again, a strong base in Europe from a customer point of view, but also from an IDM point of view, where research can link to and make then also drive innovation to commercial success. Yeah, AI. AI is a second topic in everybody's mind these days, and lots of opportunities, but also lots of challenges. Because if you think it through, the path we are on with cloud AI, with generative AI, is probably not sustainable. Why is that? It's a simple question of power consumption. And the power consumption comes from the fact that these processors, and please look to the right-hand side first, are having a very, very different power consumption than the traditional CPU. So we are talking right now about 1 kilowatt per processor, going further up with every generation from the well-known company. Now, you can create some scenarios, and on the left-hand side, it's probably one that is, stressing the point quite a bit, but it might be, if we are not counteracting that, the current power consumption of global electricity of 2% will rise up to 7%, which is a huge headache. Yes, those operators might get green electricity, but they will take that green electricity away from other areas where we also need it. So we need to bend the curve in a way in order to get it onto a sustainable way. And one thing we contribute as Infineon is how we feed the power into the processor. So first, 1 kilowatt, very simple equation, power equals voltage times current, tells you at 0.5 core voltage, these are huge currents. And it's not only the static currents that matter, it's the transients that matter most, because we have to switch these currents at a rate of 1,000 amps per microsecond. So a typical processor already today has about 40 rails, and one of these rails is shown up there on the lateral power diagram. So one rail out of 40 feeding into the processor from the side. Now at those currents, very simple, even this 1 centimeter distance, as it may be, is a source of huge power losses. So we are ramping, as we have developed over many years, because again it looks trivial, but it's rather complex. We are now ramping with first customers what we call vertical power. So it's a power module which is getting as close as possible towards the processor from underneath into the PCB. You can imagine thermal management is paramount, and of course reliability matters a lot. But alone with this measure, and that's just one factor, we could save in all data centers combined 12% TCO, meaning energy saving, which is equivalent of the consumption of Portugal as we speak. One measure only. But we need a lot more. And of course, here comes then your work into the picture. When I looked at the Blackwell announcement from NVIDIA, it came up to my mind that this 10 to the power of 16 flops at 2000 watts. There was a similar number, 1999, from Mr. Kurzweil, saying that this is potentially the capacity described in flops of the human brain, but at 20 watts, not at 2000 watts. Now, is it true that now one Blackwell with 72 GPUs and 36 CPUs is already able to mimic the human brain. No, not at all. There are other sources that said 10 to the power of 28 flops, but a lot needs to be done there and can be done there to get the architecture, which again was derived for graphic cards, into new domains, and therefore solving the power efficiency problem, because otherwise I believe we will run into a real issue, and innovation will slow down simply out of the fact that the power consumption cannot be handled any longer. Another way to escape that is, of course, edge AI, right? We don't need to do everything into the cloud. There are various options, and also the microcontroller generation I just quoted before on 28 with the RM does have features to download models which are pre-trained, but then get the final touch in the system. So we need to scale down the AI, we need to bring it to the edge, where power consumption, of course, is much easier to handle, and at a very, very different scale. Here we are talking about tens of watts and not thousands of watts in terms of CPU power consumption. Yeah, and with this, I was also asked, what are you doing in terms of AI? And I think Infineon is all over the place in terms of AI in the positive sense. We are applying AI in our factories, replacing, for example, image inspections and so on. That's in progress. Our products are enhanced with AI, as I just said. So we are not the processor company, but we put AI accelerators into our microcontrollers. And of course, our products enable AI. You saw the example of powering AI, and we also offer services related to this. And with this, I already come to the conclusion. Happy then to take your questions. So the conclusion is semiconductors is more than nanometers. We once coined the term more than Moore, which I like a lot more than what is currently used in the political landscape, legacy, foundational, mature semiconductors, because it really doesn't show the innovation which is happening in each of these branches on the tree, which I showed you. So more than Moore, I think, is a much better term. And there's a huge variety of innovation going on, and also spots where we are really leading in Europe, and that I think should be also a motivation for you maybe to consider. AI will run into problems. We are far away from green computing, because honestly, if operators are taking away the green electricity from others, I wouldn't call that green computing. We have to get the power down, and many topics are required, and I hope you will contribute also with this Congress on progress on neuromorphic chips. And of course, AI, I think we all agree that it can create substantial value for our societies, addressing our major challenges, but we need to do it in a responsible manner. Thank you very much.
Yeah, Jochen Hanebeck, thanks a lot for this wonderful talk, which is now open for discussions. So please feel free to use these microphones. Briefly state where you are, who you are, and where you're coming from. Yeah, please.
Yes, Max Lemme, RWTH Aachen and AMO GmbH. Thank you very much for your inspirational talk. I have a question about let's say, the activities of Europe in the field of neuromorphic architectures. You mentioned NVIDIA, and we all know that the large chip manufacturers are, for the advanced nodes, are either in Asia or in the US. But is there a market for Infineon or other European players to provide specific architecture, specific processors at the edge or at where you don't need a full GPU cluster, let's say?
Yeah. So again, remember these curves of exponential investments required into fabs, but also development. And I think we would be not well advised if Infineon is now going into the development and production, or not even the development of GPUs. So the industry did a good job, also supported by globalization, that we really created excellence in certain companies somewhere on the world. And of course, you can imagine this deglobalization is a big headache for us. We are absolutely committed to drive edge AI, as I depicted or mentioned with the automotive microcontroller family, but we are doing similar things on connected MCUs, on certain industrial microcontrollers. So that's an area we definitely want to push forward, keeping and advancing our stronghold in microcontrollers. The other effect is still that I think within, I have to say, the Western world, there is a huge desire to detect the next startup idea or the next technical idea. So even working now with companies in California has changed. When I started, the saying went like, you can only be successful if your customer is based in middle of Europe. And that was probably true. Some of you remember that Infineon was once into communication basebands because Hoffmannstraße Siemens built the system. And of course, we are also strong because of the automotive industry. But that, I think, has changed. We are able to cooperate with companies also across the Atlantic. We have big teams in California sitting next to customers. So it's really still a global play, but deglobalization is a headache at the same time.
Thank you.
Yeah, please, next.
Hi, this is Shankha from IMEC. So I have a question regarding the power semiconductors. So normally we see there is development in automobile industry there, but do you think AI can be also instrumental to develop more power semiconductor related research in case of RF communication or like overall power industry? Like any comment on that?
You're meaning AI to develop or power semiconductors to help in other areas beyond automotive?
So power semiconductors to help beyond automotive in the field of AI.
No, absolutely. To give you two examples, I believe, for example, that gallium nitride on silicon is going to be the material of choice for 5G, 6G communication, 5G, 6G generation communication, even if it's not from a material point of view at first sight the best material as compared, for example, to gallium nitride on silicon carbide, but the industry can handle gallium nitride on silicon a lot better. And therefore, that's one area. So higher frequency in going towards 6G will be an area. And the other area I would like to highlight in AI, the powering AI. You saw the 48 to core, right? 48 to core voltage is also a domain for gallium nitride. We have to solve some technical problems, but I could very well foresee that in that path we will eventually also see gallium nitride happening. So gallium nitride will eat into the picture more and more, and that's why, for example, we also did this acquisition last year just to double our team in order to push gallium nitride further and faster into the market.
Thank you.
Next question, please.
Hi, I'm Sebastian from Forschungszentrum Jülich. So my question would be, in this picture that you showed in the beginning, there was the mixed signal and analog electronics. a little bit branching off into nowhere without any real product in the end. So do you in the end see that this branch maybe come back into the microcontroller and probably even microprocessor regime? So do you see the place of real analog computing in normal microcontrollers?
Okay, so first of all, I apologize again for the picture. It was meant for politicians to, it has not a scientific certificate, but it served its purpose very nicely. Analog. I think there were a couple of important things going on in analog. I think we benefited a lot from the development of digitalizing analog capabilities, because if you digitalize, you can shrink, and as an industry, we need to push for productivity. Now, nevertheless, I think there is an analog space. It's not that my analog developers get fear that they get useless. The contrary. The analog computing or in-memory computing is indeed a very interesting area. It obviously would also solve some of the challenges in GPU. I see a lot of activity. We are also into that. We are looking into different materials, but it's still, I think, I haven't seen at least a breakthrough, but maybe it's around the corner. But it would be, I think, desirable in order to also get out of this bottleneck of GPU to memory.
Thanks.
Yeah, please, Max.
So this is maybe a bit of a provocative question.
Please.
We are also seeing that the automotive industry, which is extremely strong in Europe, is looking more and more into circuit design. Maybe driven or forced by Tesla, but it's happening and we're having good conversations. But of course, this is a core expertise of Infineon and other semiconductor manufacturers. So do you see that as a benefit or as a competition? Who will design the chips for the cars in the future?
Yeah, so first of all, again, like the tree, there is not one chip. I counted recently, we have 300 product groups for automotive. So the question is, which of those products are a meaningful target for an OEM? There was a notion in the allocation times 2 years ago that some OEMs thought in desperation, let's use other semiconductors or let's do our semiconductors ourselves in order to avoid these sort of bottlenecks in the future. I think a lot of realism has come into that desire. Nevertheless, there is some points, if you think about the SoC for autonomous driving, that's maybe an area, and that's where, for example, Tesla is working in. If you can really show that this dedicated architecture is creating a value on the system level, I doubt that this is true for most of the OEMs. So I would think that some will still stay in there, but not all of them. And by the way, we are not into this SoC design. We are the market leader in automotive microcontroller, which covers everything from zone control to edge computing, but not the SoC MPU level.
Thank you.
Yes, please.
Abu Sebastian, IBM Research. Very nice talk. Just one question about your, you mentioned microcontrollers and how Infineon and ST are, big players in that space. ST, as far as I know, is trying to differentiate the microcontrollers with neural processing units, like digital neural processing units, and also embedded memory, like phase change below the 40 nanometer node. Mm-hmm. Could you comment a bit on, what kind of innovations you are coming up with in the microcontroller space, similar to what ST is doing?
Yeah, similar thing. We have a NPU, sort of. We call it slightly different in the 28 nanometer generation, and out of the cooperation with Mr. Waser, we are using RM because we feel that RM is better scalable than PC RAM, I think they call it. Actually, TSMC is right now already pushing RM towards 8 nanometer. And therefore, I think we have really established here with TSMC a standard, and the industry goes right as we speak either into MRAM or RM, but MRAM has obviously some drawbacks if you're exposed to magnetic fields, which is in the car a likely situation, or if you think about smart cards. So I would bet my horses on RM.
I see. Okay. So instead of embedded NOR flash, you are going
Flash is finished with 28.
Exactly. So below that, you
yes.
expect RM to be
yes,
to be
RM
choice.
is a very good choice, and it's very cost effective. It has only 3 layers of litho layers, so much less complex than floating gate.
Thanks.
Let me ask a question as well.
Sure.
So if I look ahead, what could be coming, then we see on the horizon that perhaps the autonomous robot, the household robots, may come up. And Germany and Europe should be strong in this because we have a very strong mechanical engineering, which you need. And we have got the microcontrollers, which we need there, and as well also the power electronics. How do you see the vision? Because there's no product yet. So all the products which I see on YouTube and so on, they are from the States or from Asia, but nothing from Germany. Why that?
Yeah, true, because I would guess the real challenges are maybe beyond the hardware and into algorithm and into software. But you're right, I would also count that as one of the very interesting areas for us to work. And I mentioned the example of small motors driven by gallium nitride, especially for this humanitic robots. And you're right, if I think through my space of customers as of today, they are either mainly US and somewhat Japanese, but indeed an area, and that would fit very nicely to other competences we have in this country. And that's anyway, I think, even if I say that we can interact and work and cooperate with companies in California, and we have to do this as a global player, but for us in Germany, from an economic point of view, it's paramount to develop ecosystems, industrial ecosystems, and we all know that some ecosystems which were the base of the German economy, or also the European economy in the past, are getting weaker. We need to develop new ones to keep the economic development.
Yeah. Okay, thank you. Please.
Yeah, hello, my name is Christoph Reich. I'm from a German funding agency. And I would like to change the topic a little bit. At the moment we have like a chip war worldwide, so we have a race for public funding. In Europe we have the European Chips Act, we have the IPCI programs. Yeah, and I would like to know how important is this public funding for you to actually survive in Germany?
Yeah, it's essential. I'm not a person that is calling first for funding, but if I look around, I have to face the fact that from Taiwan to Japan to China to Korea to other countries in Europe, but also US, everybody has identified the semiconductors as a strategic industry, which has a huge network effect, maybe more than other industries, into industries, and some of them were just mentioned. There's even numbers, how much of GDP this industry is driving. The industry itself has 500, 600 billion, is going towards $1 trillion at the end of the decade, and that this industry has a huge effect. So from my point of view, it's right that also in Europe, we came to the conclusion, not only out of the allocation, but of course the allocation worked as a catalyst, that this industry is important also to bridge to the previous question, to create a new ecosystem. Now, if I look at the worldwide map, without the support we get also from the German government, we would definitely not be able to build the factories, at least not to the scale and not to the portfolio width which we are doing right now. We would probably depend more on Taiwan. We all know that there is a potential threat, and therefore we appreciate, even though I fully understand the public discussion, that this is a lot of money for one industry. The numbers per employee are a little bit distorted because the network effect is a lot more than towards the people we employ. It's easily a factor 5, if not even more. So from my point of view, it's a good investment. And that's why we are driving this very much in Dresden with our own investment, but also was for me really a pivotal moment when TSMC agreed also to come to Dresden, because I think there is going to be the base of the European semiconductor ecosystem.
Thank you.
Please.
Yeah, good morning. My name is Michael Heuken, and I'm from Extron, and you may know we build this beautiful MOCVD equipment. And
we have a few, yeah.
Yeah, good to see a satisfied customer. My question is regarding the future. So you are talking about generation 3 semiconductor, gallium nitride, silicon carbide, silicon of course, but there's a new class of materials on the horizon, the 2D materials. Again, with unique properties for AI applications, for memristors and so on. Can you comment on your position there, and what are you doing to get this new trend and make it useful for your...
What do you have exactly in mind?
MOS2, for example. So these are graphene-like two-dimensional semiconductor. So they have weak van der Waals bonding to the substrate, so you can delaminate them, you can make flexible electronics, you can do memristors and all these kind.
Yep.
So some people say they may replace silicon as a channel material and so on. So some people say, so the big ones say, oh, that's maybe the big future for the so-called silicon industry, which may become a 2D industry.
Yeah, actually, the industry is absolutely into 2D, but more from a stacking point of view, right? All the nanometers you have seen in the main Moore's path is no longer geometry, but due to stacking. So 2D, heterogeneous integration, all of that, I think, is ongoing. Honestly, on many of the new materials, I think the industry has changed over the last 30 years. When I started at the time with Siemens, there was still a central research team, right? And not only Infineon, but the whole industry, and if you think about IBM, Bell Labs, all those places where these great innovations took place, I think this is no longer the main path of these topics to emerge. It's rather through startups, and we are building up a structure where we want to screen more startups and see what's going on. From a company point of view, it's sometimes a lot better to feed startups, also to integrate startups at a certain point in time, other than to put R&D money directly into all these ideas, because there's so many, and the likelihood of failure is accordingly. Yeah, but it's all, I mean, I'm an engineer by heart, so all fascinating stuff. I just need to also look to finance it.
Thank you.
Yeah, next question, please.
Good morning, Stefan van Waasen, Forschungszentrum Jülich, and I also worked only 12 years for Infineon some time ago. Yeah?
Okay.
Okay, so one question, I would like to change the topic a little bit, because one asset is technology and fabs, but the other asset is human resources.
Absolutely.
And you are coming here from RWTH. So how can you support, or how would you like, or how are you supporting education? Because with the ramp down of semiconductor industry during the last decades, because this ramp up is now very fresh again, we lost many people in that area, and let's say microelectronics is not the most, it's not the most interesting topic for the students any longer. Everybody is doing software, that's nice, but hardware without software without hardware is difficult. And I do not really believe in that AI takes over it completely to do the development. Yeah? So what is the position of Infineon there?
I share that view. I think AI can support, but we will need people mentioned. And actually, that is one reason why I'm here today, because right afterwards I will sit down with some students to motivate them for microelectronics. You're absolutely right, and the challenge is manifold. Let's start maybe in the clientele you have not in mind, but I tell you, one of our biggest challenge right now in the area of Saxony is to get the maintenance people. If you invest these sort of assets, the one thing you want to make sure is that they run 365/24. And we are making a big effort with the state of Saxony and others to build up an academy to train people on this technician level, which is absolutely paramount to run these fabs. And of course, it goes all the way towards engineers. I think here the area where we can draw on is bigger. Obviously, typically engineers, especially maybe in the early years of the career, are more flexible. But I want to nurture the relation also with Aachen here. We have many university corporations towards Italy, Austria, in the southern part of Germany, but I think there's more can be done here with Aachen, and that was one of the motivations for me to come today.
Thanks.
Yeah. So, are there further questions? If that is not the case, then let's thank Jochen Hanebeck once again.
Thank you.